Okay, so last topic in random numbers is stat. I'm going quite fast. So let's simulate Ising phase transition. Okay, so some of you may not know. If you're not in physics, then you probably don't know the phase transition. But let me just give you an idea. Okay, so these are spins. Okay, this blue spins. It can be either up or down. Okay, they are on a square grid. And there are many of them, right? I mean, for me, it's much easier to plot 5 by 5, but my code, I think, is 50 by 50 grid. If you work with more, you'll get a better result, 100 or 1000, but it'll take longer time. Huh? So you can see the spins. Some are up, some are down, but they are basically random. And these are up, and it's not even systematic up, down, up, down, up, down. Okay, so this is called disordered phase. Here, all of them are up. It's possible that one of them could be down, okay? Okay, but this is ordered phase. So in real life, what do we find? This system, at high temperature, all the spins go crazy. Okay, they just heat it up. They are like they're drunk. They just some of them are up, some of them are down. Okay, so that's disordered. If you cool them down, then because of interaction, I'm going to show you what is meant by interaction. Because the interactions among these molecules, they either the spins, either they line up or line down. Okay, this system is the one I'm talking about. Ising spin is equally probable to either go up or down under transition. Okay, and this is called transition. At some temperature, they start lining up in one direction. Okay, so this is called phase transition from random to ordered. Okay, liquid, so liquid will cool down, it becomes solid, like ice, it becomes water, water becomes ice. So that's the phase transition. So water, the molecules are somewhat random, moving randomly, but when you cool it down, all of them become a crystal. Okay, or gas becomes liquid. Liquid is not as ordered as solid, but well, I mean, it's a phase transition. Okay, now the interaction for this system is called SI-SJ. Okay, so S is a spin, which can take value +1 or -1. Okay, so but this product is done only for the nearest neighbor. Okay, so this spin here, I compute this energy. Okay, so this energy of the system. So what do I do? This spin, I take the nearest neighbors, the 4 of them. Okay, but don't take the diagonal neighbor, only the face neighbors. Okay, this one, this one, this one, and this one, and you compute SI-SJ. So this multiplied by this multiplied by that. So either it will take value +1 or -1. Okay, if it is disorder, then half the time it will be +1, 1, 1. Okay, or -1, -1. But it could be 1, -1 will be the product is -1. Okay, so right now what will I get? In fact, for this particular case, this will be -1. But these will be also -1. No, sorry. This is +1, right? Down, down. This will be -1. This is -1, and this is -1. So there are 3 -1 and 1 is +1. Okay. So it's a disordered phase. So it's likely that 2 -1, 2 +1 in total disorder. Okay. So I do the sum. If disorder, then basically you'll get 0. Well, this J factor. This is a coupling constant. Coupling constant is a positive number. So energy. Okay. One more physics principle, that systems like to have lower energy. Okay. So if J is positive, then lower energy will be when all these guys are in the same direction. Okay, either so same direction, SI-SJ will be positive number. So lowest energy will be then all of them are lying in the same direction. Either could be up or down. Okay, this is the up-down symmetry is called. Is that clear to everyone? This energy function determines the state and temperature. Okay, so there's a temperature as well. So if the temperature is too large, then it will try to excite these molecules, or not, I always say molecules, this spins. And okay, if so, interaction is basically ineffective if it is too much of heat. But at lower temperatures, temperature is low, so this random push or random noise is not as effective. So they try to line up or line down. Okay. So this energy. Okay. Now please wait. This bit complicated. So you have to just wait. So we also define a function, average magnetization. So this is called M is magnetization. Okay. It is basically the difference between, well, basically M up minus M down divided by total number of spins. Okay. So if M down is 0, okay, all of them are up, then I'll basically get this to be 1, right? Plus 1. Imagine that all of them are down, then M this becomes 0, and everybody is down, so it will be minus 1. Okay. So magnetization for ordered phase either is plus 1 or minus 1. For disordered phase, totally disordered, M up equal to M down, so the difference will be basically 0. Okay. So the number of up spins and number of down spins, that is M up and M down respectively. Okay, so we'll measure for given temperature, we'll measure magnetization. Okay, but it turns out that it's a random system. So the given temperature, at some point it is up, there's some particular spin, let's say this is up, but if you wait for some time, then it will become down. If it's low temperature, then it's kind of flipping is hard. But at high temperature, they keep doing randomly. Okay, it's a dynamical system. So some of you probably, if you're not done physics course, you'll be slightly at a loss, but just treat that as a story. So this is not part of the, I mean, I will not ask this question, but I'm doing it for completeness. So this probability of given configuration, this is a configuration. This is a configuration, okay? This is also a configuration. But at a given temperature, how likely is this configuration? And how likely is this configuration? Any configuration, it can be when some are up, some are down. So we compute energy EA, this by this one, and so this energy is computed by the function minus J is SISJ. Put a minus sign by KBT. KB is a Boltzmann constant and exponential. Okay, so compute this, divide by the same thing, but you do it for all configurations. Okay, so if there are n particles, then it will be 2 to the power n configuration, right? It can be up or down. Okay, so 2 to the power n. So 50 means 2 to the power 50. Okay, this huge number, but you have to compute this sum, and you do that. So that's the probability of a configuration. Okay, this is by Boltzmann. Okay, this is called Boltzmann distribution. At low temperature, okay, it turns out at 0 temperature, I mean 0 Kelvin, it will be advantage. I mean, basically, all up or all down will be the most favorable. In fact, that will be only state. Other state will be lowest energy will be the only state. But higher energy, higher temperature, more energy also becomes equally like. I mean, not equally likely, probable. So this KVT is coming below. So at lowest temperature, this becomes infinity. Okay, times EA, and here you want EA to be the lowest to get to the finite probability. So only the ordered state is the only possibility at 0 temperature. 0 Kelvin, not 0 Celsius. Okay. Now, if a two configuration E and EB, then the ratio of probability of E and EB will be this, because the bottom will get cancelled. So E alpha minus E beta. It's not AB, alpha beta. Okay. E alpha minus E beta by KBT. Now, so it turns out numerically, suppose I want to compute the probability of a given state, then ideally I would like to, Boltzmann says you have to compute all possible, you have to figure out all possible states. There are 2 to the power 50 of them for 50 spins. Okay, if 50 by 50, then it becomes 2500. 2 to the power 2500. Okay, it's a huge number. If I do it, my computer will crash. It is not going to do it. Okay, so that is where a clever algorithm comes, which I'm going to tell you in the next slide. So the idea is that if I said, if the lower energy is there, then it is more likely. So if E beta is less than E alpha, then I take with probability 1. Okay, I just say that, okay, this is a state I'm going to take. Okay, so I'm not sampling for all states. I sample on more likely states more often. Okay, so this is an approximation. So this is a Metropolis algorithm. Okay, and we more likely states are sampled more. So you'll basically instead of sampling this many states, I'll sample much lower sample. But still, I will be getting answer close to the real answer. Okay, and okay, so if E beta is less than E alpha, then you choose that state and compute energy. Okay, compute magnetization. I need average magnetization. Okay, that's what I want. If E beta is greater than E alpha, then you don't say that that state is not possible. Okay, that state is possible, but with the probability this probability. This is the Metropolis algorithm. So you apply this logic. So here, this is the algorithm. If given configuration, compute the energy E alpha, then randomly pick a site ij and flip its spin. Take a random site. Compute the energy of the new configuration E beta. If the new energy is less than E alpha, then accept the configuration as the next configuration. But E beta is greater than E alpha, then accept the new configuration, the probability, this probability. E beta minus E alpha by KBT. Okay, and repeat this process from 1 until average magnetization saturates to a constant value. Okay, so this is algorithm. Okay, I hope it is clear to most of you. So I had to do a loop. Okay, so I run a loop. I start with some random configuration and compute energy or magnetization, and flip arbitrarily, compute the next energy. And if it is energy is more, then I'm not going to choose all the time. I choose only less time. When it is less, then I choose always. Okay, that's more likely. So what do we go? So this is the number of iterations. Okay, so I ran it for 100,000 time steps. So this is a normalized temperature. Okay, so this temperature by kBT by J. Okay, so that's average temperature. This is T bar, not average. This is a normalized temperature, non-dimensionalized. So if T bar is equal to 1, I get magnetization to go to 1. This is blue one. Okay, so that means it's all up. T bar equal to 2 also, it is going up. But T bar equal to 10, it is going to 0. Okay, so it is transitioning to ordered state. This is basically order 1. Okay, right now they're all up. Now, at some point, T bar, there is a transition from disorder to order. And that I don't remember right now. The number is something like 2.5 non-dimensional unit. This one. Okay, I should have written it, but it's not written here. So, by the way, when you go closer and closer to the transition temperature, this will take longer and longer, and that's why it's a project. Okay, so you really have to run it for a very long time, and you just run the same code, okay, which is given to you, and you'll find that this will be going slowly into that. It will just go very slowly to 1. If it is less than that critical temperature, it's TC. If it's above the temperature, and very slowly it will go to 0. Very slowly. Okay, so this is called critical slowing down. Critical slowing down. When you go close to the T critical. Okay, so that's why it's a project. So you have to do it for longer time. If you can speed up, well, better, but that will require parallel algorithms. Okay, I don't know whether you know it, uh, but if you're running on your laptop, it will just take long time, and your grade will depend on how close you are. Okay, so